Good afternoon. Welcome to the Geospatial Forum. I'm Ross Mintermeyer, Director of the Center for Geospatial Analytics, and it's a great pleasure to have Dr. Gustavo Machado here with us today to speak with us in the forum. Gustavo is an assistant professor in the College of Veterinary Medicine, and he is our first and to date only faculty fellow in the center from the College of Veterinary Medicine. So it's great to have him and his expertise with epidemiological modeling and of the spread of infectious disease and things like that. It's also exciting for me to welcome our next year's incoming cohort of geospatial PhD students. We have 11 students here today who'll be joining us in August, and it's really, really wonderful having you all here. So I look forward to all the activities over the next couple of days. And I hope you enjoy Dr. Machado's forum.
Thanks so much. Thanks. Thanks for the introduction, Ross. And it's a pleasure to talk to you a little bit of what I've been doing the last few years. I'm originally from Brazil, so my accent is a little heavy on that. And I'm going to walk you guys through different skills. So I'm going to be walking through a small area approach, which is basically aggregating number of cases in a polygon, and then modeling the process on that scale, and then moving to more geostatistical approaches, which is where we are trying to move this research forward. I'm going to talk to you about the study area, and the study area is in Brazil. So if you've been to Brazil or you heard about Brazil, what comes to your mind is Rio, right? It's a nice place to go, have nice beaches. Depending on the holiday, you might be fighting for a piece of sand, but other than that, it's great. So Rio is situated, let me go back. Is situated, let me see, where is the pointer here? It won't, okay. So yeah, basically, let me use the mouse. Yeah, that's great. Yeah. So Rio is basically in this area, and if you're looking for a place where it's not as crowded, you want to go move south. If you move south, you might find beaches that is not so crowded, but still, it's a very nice place to go for a visit. And if you're looking for study emerging diseases and special tropical diseases, we have a lot. And a big contrast of these nice areas are the things that we see here. This is an image from São Paulo. So we have the metropolitan areas, and there is just jump between rich or more developed areas to the favelas. And the favelas, we see a lot of emerging diseases, and especially tuberculosis in human, we have a lot. Leptospirosis is the topic today. We see a lot happening there, so it's very hard to tease apart the risk in these areas because the data that we are modeling is into the polygon. So we don't have very good sense of the location here. So we start looking more at the regional level to try to understand the process. Not very easy to do it. So we're gonna walk you guys through that. And if we go to the northeast part, we have areas that is super poor, where basically people don't have any water that is treated, and they are very exposed to the environment. So those areas are a big risk for lepto, for TB, for a lot of things that are transmitted through the environment. Okay. So here is just a little video on what happens when we have summertime, and this is actually downtown Rio. So there is not the favela, but you can see that with the rain and the amount of water that we have in these regions, they actually enter to the buildings, and people that are not supposed to be exposed due to poverty or due to restriction on income, they are also exposed to the risks. In this case, the water was just flushing to the area, and I can highlight not only lepto, but other diseases that are vector-borne diseases might have an impact, might increase circulate in these areas. One example is dengue. Dengue is believed to be associated with the summer cycle, so there's a big seasonality effect there. In lepto, we don't see that much. We're going to look more in details on that. So, and the other problem in this area is that we don't have a very good forecast Our forecast is worse than here. So here we have a good forecast for the weather. So people can be cut off going home without knowing that the rain is coming, and they might be just trapped somewhere, and the only chance of getting home is to be exposed to the water. And this water carries all the trash, all the garbage, and goes through the coast. So we expect to see more cases in the coast in human because of the exposure of these waters to that population. So what is lepto? Lepto is a zoonotic disease. In the environment, it's hosted by rodents. In Latin America, we have this very cute large rodent that people are hunting now. We can hunt that down there. It's legal right now. And they can carry lepto as well. So normally, they shed the lepto in the environment, normally in the water. And if you are exposed to the water, these tiny bacteria, who actually we have more than 100 serotypes, can enter your skin without a lesion. So if just exposed to the water is enough to catch the disease. We also have the domestic part here associated. We have high densities and high incidences of lepto in cattle and horses and dogs. So people who work with those domestic animals are also exposed. There is a story that is not so happy. A colleague of mine last semester, she was treating orally a dog, and she had her nails done on the same week. She got infected with ichthyomoragica, is a pathogenic serotype, and she passed it. So even people that are supposed to be trained get infected and die from lepto. In the US, the incidents are low, but we still have it circulating. So the domestic animals, they can also shed it back to the environment, and then people who actually are exposed to that water body again can be reinfected, or if people who work with farming, we can be exposed to the bacteria in the kidney, so it circulates and stays in the kidney. So if you're working in a slaughterhouse, if you're a vet, or if you are just a helper, you're supposed to be wearing APIs, and normally that's not the case. Have you been to a slaughterhouse before? Anybody? It's not very a place that you want to wear API. So normally you are exposed to that, and we have not a very good sense on how many animals are infected. There is no mandatory test for the animals. But lepto is mandatory to report in Brazil. So it's a negative disease, but it's mandatory to report. So every case that is suspected, there is a pipeline where we define this is a really a case based on lab work, based on clinical science, and then this is reported to the central office, and they keep track of what's going on in the whole country. Okay? Questions?
Lepto, can it be if you consume meat of an animal that is sick?
Very, very difficult. You need to get into your stream, into your bloodstream. So if you have a little cut and you're touching the organs, or a kidney, for example, then you can be infected. Or if the bacteria is in the very early stage where it's circulating the blood of the animal, and in this example, my colleague, she got the nails done, so she had a crack on the skin. So it's very rare that to happen. So at the beginning, they treat her for dengue. It wasn't dengue, it was lepto, so they treated wrong, and then it was too late. So eating the food is not, there's no case that I am aware of, okay? So this is every year. So we see here this happening throughout the coastal areas, but also where we don't have big rivers. The flooding is something that brings the water up, and then the rodents are displaced, and they tend to spread, and we tend to see disease spreading throughout the city when this is happening. And it's not rare to see this situation here where we have the domestic animals very in close contact with the human, and this is in a poor area, so they really don't believe that the water can kill them or they can get any infection if they're exposed to these water bodies. And if these kettles are positive, they might be shedding some amount of lepto in the environment, and you might see an infection happening here. And the worst is where you cannot do anything. The flood comes, all you have to do is just wait until the water goes down. You have to walk to the water, be exposed to the water, and really they don't have information or don't get information enough that this is risky for lepto. So I'm going to walk you guys through these, and this was a request. We got a small project with Ministry of Health in Brazil They gave us the data of 17 years of data of lepto, and what you see here is the incidence across these years by municipality. We have 564,000 municipalities, and you can see that there is some sort of clusterization on the cases by the coast, but we also see cases in this area in Amazonia where it's very humid and very hot, a lot of rivers around here. But what they want to do is to classify the risk to the whole country. So they want to merge the programs of visceral leishmaniasis, leptospirosis, dengue, and other diseases that are communicable, and come up with a list of priorities. Which municipality, which areas they should do something about it. And this country is very large, so we're trying to help them to do that. So to try to answer this question, we look into the data, and what we saw was that over time, over these 17 years, more or less the incidents are constant. We see some spatial pattern. There are some states that have more cases than others. So you can start thinking about some spatial structure here in the cases. Wasn't very clear. When we see mortality, you can see that mortality is also not improving. So they are doing things. They have the treatment. They are making people aware of the cases, but you can see mortality is kind of static here. And what you're seeing here is average lethality by 100,000 people every year. It's not very clear the spatial structure of the cases neither. If we look per state, so we have 27 states, we can see that one state here reported a lot of cases, and this is the standard incidence rate, basically the number of cases divided by the expectation on that state on that year. And you cannot see a very clear pattern. Of course, we have higher values here, so it's hard to see what's happening in the other states. If we look at the mortality, you can see mortality happening all over the place, but really we don't see a specific state that we should focus our effort. Right now, the effort that they are doing, they are just counting the number of cases, and you have the max number of cases, doesn't matter the population. They put money there, they transfer people to work with lepto in those regions. They do advertisement in radio and in TV to try to bring awareness to the people. But they see it's not working, so they want something better. And then the question that we got from them is that can we identify the spatial structure of risk for lepto in the whole country? And if we can identify that, is that some spatial temporal structure on the risk? Something's happening over time and over the region. And if that's possible, can you give us a priority index, or can you help us identify some priority areas where we really can do some measures to try to control the disease? And then the other question that came is that until which resolution we need to go to have a model that is working, okay, and a resolution where they can do something about it. So we started by the state, okay, just to see where the risk was in the state, and we use one type of model for this. Then I'm going to walk you guys through it. I don't want to get too much in details here, but basically what we are modeling here are the number of cases. So offset here is the expectations. Expectations calculated by the incidence in one state, in 1 year, in the whole country, multiplying the observed number of cases for the incidence. So we're going to have the expectation on the cases. So we are dividing the cases by the expected. So indirectly we have an incidence rate. Why incidence rate? Incidence rate doesn't suffer for high values. So these kind of models, they are very sensitive to high values. So if I have 100 cases in one location, 0 on one and the other location, you're going to be over 50 to that location. So we don't want to see that. That's why we're modeling the standard incidence rate. So we start with the states. We have 27 states and we have all the years. We assume that this data is Poisson distributed, and we are trying to estimate this parameter, which is basically depending on the observed cases in the space and the time, and we are offsetting by the expectation, by the expected number of cases. And this is a Bayesian approach, so we're going to have some priors. We don't have a very good knowledge about these parameters, so we're going to assign some non-informative priors. Questions? Anybody saw this kind of model before? ICAR models, anybody is familiar with this? Have you heard about it? Some people? Okay. So you can see here that I have an intercept, which is basically the average number of cases throughout the whole region. And then I have a couple of random effects here. I have 2 on space, 2 in time, and 1 interaction. Just briefly going to talk about those so we know what they are trying to capture. And then we're going to have some covariates that are risk factors. So we believe that temperature, precipitation, and socioeconomics have some sort of spatial structure, and we try to capture that and try to map that as well. So on the spatial side, we have a joint distribution on the structure effect. So basically, these random effect is trying to smooth the risk in the surface. So if I ask you guys to raise the hand if you think this room is very hot. Just raise your hand if it's very hot, it's cold, just put your hand down. Who think it's very hot? You don't have, huh?
It was a few minutes ago.
It was? Okay. So the idea of asking is that is if you say that it's very hot and your neighbor doesn't say that it's very hot, maybe is something wrong, right? Because the distance between your location is not that far, or there is a dependency on the risk. So in this case, normally what you do, you look to your neighbor and then you, okay, it's too high, just gonna put a little bit down. It's the same idea here, okay, for this effect. And I'm gonna give one example. And then the structure effect is just gonna capture everything that is noise. That the structure effect is not capturing, this random effect gonna capture. Basically, this effect gonna capture the latent process that is not explained by the dependence on the neighbors in this region. And this effect gonna explain what is dependent on the neighbors on that region. So if I highlight here one location, and this is Acre, one state, and it's sharing 2 neighbors. So it's just accounting these 2 neighbors. So basically the structure effect is trying to average the risk that we don't understand very well, is captured by this random effect, to estimate the risk on this area. So we're trying to smooth the risk here. If this random effect is important, the variance explained by this component can be high. So if that's high, we can guess that there is some sort of special structure in this space. And we are trying to understand why and what kind of risk is that. 2 random effects on the time as well. One means that we don't have a long trend on increase of the risk. It's just things happens isolated in some areas and we don't understand very well. They're going to be captured by this parameter, which is just a random effect that has no temporal structure and time. And then we have one that is structure effect, which basically says and going to capture if we have a long trend, things are happening, and it's happening because something happened this year, happening another year, and we just see increase or decrease on the risk. And then we're going to also allow some interactions. We're going to interact these parameters. So we're going to allow 4 type of interactions here. Just going to explain the last one, which is basically this is the structure effect and this is structure temporal effect. By the model selection, if this is the best model, the interpretation of this is that there is something that happened in space, so there is something that happened in that state, which is important. There is a structure risk on that state, and it's also depending on what happened in the year before. So it's dependent on space and time. Now, if the interaction is just a random effect in the space and time, means things are isolated. Something happened in this moment that's important, then next year something else happened that we cannot understand very well. So those are the models that we fitted, and we're trying to select the best to try then to predict, to understand the posterior of the risk, which is this parameter here. Okay? Too easy? Very straightforward, right? And then the priors, putting just a non-informative prior in the intercept basically is a line, a flat line. I don't know how much is going to increase or decrease, just a flat line. And then I'm assignment log gamma, which is a standard as well, for all the precision, all the parameters, all the random effects. And then model evaluation, DAC. Have you heard about DAC, students? DAC, normally used to select model by complexity, so lower the number of DAC, the better the information. We didn't lose a lot of information. And then we also calculated the predicted p-value, which is basically trying to see if the model is predicting what is observed. So based on the number of cases, what we are observing, what we are predicting, are similar. So if the distribution is to the tail of the distribution, to the close to 1 or close to 0, it means the model failed to fit to the data. We need to do something. Hopefully we can do something. We don't have to do that because it's very hard. If that doesn't work, it's straightforward, then it's start crying, trying to fit something there, okay? Change the parameters, change the precision, change things, so we are a little bit lucky here. So these are the models that we fit, okay? We started with a new model, just a random effect on space and time, and then I put the other two parameters which are on the structure on time and space, and then I allow all the interactions, and then we tested also different likelihoods because we might be overfitting these models to the data, and then we did the model selection based on those two parameters. And then we magically approached to the final model, which is basically we have a DAC and a p-value, so we can see that this model, this structure, capture the risk the better, and those p-values are very low, means the model fit the data quite well. So we are not very concerned of the fit of the model. And here are just a check. Here we are plotting the observed in the predicted number of cases, basically it's the rate. Almost too good to be true, almost a perfect line, and what you can see here is the p-value, so we don't want to see this density here and close to 0 and close to 1. This indicates us that some areas the model didn't capture very well the cases. Okay, so those two are the things that we use to select these models. And then, as I started saying in the beginning, we want to try to explain and see if this risk, we have something that they have a spatial structure or has a time structure, and we calculate the percentage explained by each of these random effects. And what you can see here is that the random effect on the space explains 66% of our data, means things are happening isolated in some areas are not depending on what's happening in the neighbor. So if something's happening to the neighbor, then we would expect to see a bigger percentage here in the structure effect. But overall, if we add those together, we can see that most of the variance is explained by the space. So there is something in the space that is important, okay? And you can see the interaction here. The interaction here has some 20% of the variance. Not very big, but the interaction here is between the two random effects, so it's very hard to explain this. One explanation for this would be that the clusterization of the cases are happening across time, they're happening in the same region. So we see one area have a high risk here and high risk here, and the next year is the same. So we're going to plot this out and see if that's the case. But the easier to understand and to explain is that there is some risk in the space, and we can actually map that, and we can try to identify risk areas on when we are trying to estimate our posterior here. And this is important to consider because there is something happening in specific states that we need to look more carefully. If I plot out this delta, the delta is basically the interaction. You can see I was trying to explain that, for example, these two areas, and for these years, they apparently have the same amount of risk associated, means we understand, we can explain that they are near each other, so it's capturing by the interaction. But over time, we don't see a very clear pattern, so we didn't explore it further, and it's very hard biologically to interpret this parameter. And then if we plot, for example, the posterior of our estimation, which is this guy here, you can see that there is one area here, this state has very high posterior mean values, means the risk in that area is supposed to be high. And if we want to try to really guide, and the idea was to guide the country to areas where they could prioritize. So we can calculate the exceedance risk. Basically, it's taking this distribution of this posterior here, and then calculating the exceedance risk. Basically, If you remember what is odds ratio, anybody know what odds ratio means? Risk rate, more or less. So risk rate or odds ratio is basically if you have things that are below 1, means the risk is decreasing. So we have a decrease in the risk. If things above 1, above the expectation, then we have an increase in the risk. So in this case, we are just cutting the distribution based on that, based on 1. So if it's above 1, we mean the risk is going to exceed the expectation. So we should do something about that if we are trying to prioritize regions that we want to do something about it. And we communicate this to the stakeholders, to the Ministry of Health, and they were not very happy because they have some issues understanding what was exceeding risk, what was posterior means. Understandable, they are most of them are on the political side. And then we provide them actually the risk rate per state, the fitted values, which is posterior of this, the exceeding risk, and they say, can you give me something more easy to understand that I can communicate to anybody throughout the country? Say, sure. So we basically just use what we already calculated, and we did this. We use PageRank. If you Google things in PageRank, this is what PageRank does. It's gonna go look for the max value of something and gonna divide the observation by that. So, for example, we divided the exceeding risk that we calculated here by the max exceeding risk in space and time. So let's say the max exceeding risk was 10. 10 divided by 10 gonna be 1, and then we just multiply by 100. So that area and that year will be the priority. So very easy. It's just a rule. Just make a rule from 0 to 100, and then they can say, this state is top priority, the other ones, we don't care. Okay? So we communicate that back to them. They say, cool, we can use that. So they are trying to use this now. This year, we are producing the maps for them, and they are trying to use this to assign money and to assign people to work in these states. And here's the priority. So we provide these maps to them as well. They say it's easier for them to see. We also give them a table with a list of the states and the priorities, and then they can see that. But also, we, as I mentioned before, we want to try to understand some risk factors. And this is a diagram. If you're going to design an ecological study, you should start with the diagram before you start flushing covariates in your model and just see what happens. Normally is what we do, right? We just download some layers, some rasters, start fitting the models and see, okay, this is telling me something. But we went to the default of what you should think about and come up with the hypothesis, and then you test them. So in this case, morbidity is the number of cases of lepto, okay? And after revisiting the literature, we say there is a direct link with temperature and the cases. We also say there is a direct link with temperature and the cases, and then there is a backdoor here, basically increase the temperature, increase the rain, the soil moisture going to increase. And this disease is actually surviving the environment, so we are also trying to test the effect of soil moisture directly in the mortality. On the other side, the data that we had poverty, illiteracy, and waste management, so trash collection. We know that rats, they like to be near to the trash, so we had this information at state level, and we did the same. Poverty directly correlated with the cases, and maybe some backdoor here. We were very sure. So we have this blue line means we disclaim that we have something that we didn't capture in the environment. We describe that, but we couldn't test because we didn't have the information. So it's very important that when you start to test hypothesis, first you think about it, and then you design your diagram, and then you go test the hypothesis. Just not start throwing covariates and see what sticks, okay? That's normally what we do. And I have a confounding factor here in dengue, because dengue is the clinical signs very similar to lepto. Question here? Diagram, very cool, takes a week or a month or 2 months or a year to design. So, and once you design, you very stick because you're not going to fit all these models again. Here is how so this is precipitation per the country, and we are centralizing to the mean because we have different units in these covariates, And if you don't have numerical issues, we need to centralize to the mean. So we centralize everything to the mean, and the interpretation of this at the end would be an increase of 1 standard deviation, how much the risk going to increase or decrease. So we centralize all the covariates. You can see northeast, this is tropical area, more precipitation. Temperature as well, we have some warm weather on the northeast, cold weather where I come from. We have snow, okay? We have snow in Brazil, believe me. Depending on the year, we have snow on the mountain, so we have winter. Poverty, we have more poor people on the north part. We also have illiterates, as also in northeast, we have more people with less education. And the waste collection, where we collect more, this is the amount of trash that is collected in every year in each state. Where we have more wealth, they're collecting more trash. So there is some indication that we're going to capture some spatial risk, or the risk going to have some spatial structure, and we're going to be able to capture that. And then I'm not going to walk you through all the models, but those are the models that we fit. So we tested the hypothesis here, and if you look back to the diagram, my diagram have temperature direct to morbidity, but temperature indirectly to the soil. So this translates to this. So this is the model that we select based on the structure of the cases, and we compare just rain directly with the base model. If the variance of explaining this with this parameter gets better, is an indication that rain is really a good predictor for the risk and has a structure that is the same as the cases. We did that for temperature, the same. And then here, you can see I put in red, those are the backdoors, so I cannot interpret those parameters, those posterior I cannot interpret in the end, because I'm only testing the direct association with soil and the risk for lepto. Okay, and we did that for all the things that we decided to do. And then at the end, we did the full model with all the covariates, the social part and the environmental part. And again, the backdoor I'm not going to be able to interpret, and the other ones, the dark ones, we can interpret. And here is the risk factors. Everybody knows risk factors, right? In this case, what we found was that an increase of 1 standard deviation on the soil moisture, so more humidity, more risk for lepto on the state level. If we increase the education, if we could increase education by the state, we will reduce the risk of lepto. And if we increase the collection of trash, we could also reduce the number of cases. They were very interesting at the beginning, and the idea, what they want is, can we simulate scenarios to see how much we need to collect more trash and how that's going to impact the incidence? So we are working on that right now. We're trying to simulate scenarios to also guide them to take some actions, not only do surveillance, but take actions to reduce the impact of these risk factors. And dengue, is just baseline, so we didn't really interpret that. We're just controlling for dengue. Cool. They like it. We provide them some reinforcement in disease control and surveillance. They are spreading funding to these areas, but they don't have money to go to the whole state. It's just too large. The states are very large. So okay, cool. We're gonna change the resolution of the data. So we move resolution, and now we started to model at the micro region. So we have 557 micro region. And these micro regions are the health unit region as well. So they have total control. So this is state, which is the best state in Brazil. Okay, if you go to Brazil, go to this one. It's the best one because I'm from there. Basically, they have control of the funding. So the central office is sending money to them, and then they can distribute between their regional level. So each of these regions has at least one vet and at least 2 physicians that takes care of diseases in general, all the diseases, not only lepto. But they can then leverage more people to work in these regions. So that's why they did in 2017. They moved people to the regions that they have more diseases overall, and also have more risk for the disease. We did the whole process again. I'm not going to walk you through all these models, but what you can see here is that now at this level, at the micro-region level, we can see that the structure effect, or the variance explained by the structure effect, is much larger, and we still have some interactions here. So this means that we should see clusterization on the risk. So you can see the risk is large, and there is some cluster there that is translated on this parameter here, basically. Okay, and what I'm showing here is two maps. One is just no covariates, and the other one is with the covariates. And you can see that the shrinking of this is accident risk. So you can see the shrinking of the accident risk means the effect of the risk factor still holds in this dimension. So you can see that we are fitting better a model if we consider the variables at this resolution. And then we also provide them the priority index. So we are giving these maps to them every year. So they can also have the list now by the region. They can go to the region and do what they can do. Control rodents, do the surveillance, and bring awareness to the people. And then they say, okay, cool, can you go further in dimension? Say, not a problem, but a problem. So the problem here, when we try to model the municipality, we have 5,564 municipalities. One is computation. This model is very complicated. It takes a couple of weeks to run. The fit is bad. You can see I just put here, we are predicting a lot of cases, big rates where we have 0, which is not a good sign. And in addition, the risk rates are very low. So average risk rate is 1. So if I increase the risk rate by 0.2, 0.3, gonna exceed already the expectation. So you're gonna change this every year. And the model is not gonna say, oh, stop, we cannot go that dimension. Let's go back to the microregion, and that's all we can do. But then they came, and the best state in Brazil came to me and say, can we do something about our state? Say, not a problem. If we have the funding, we can do. So we moved to a different dimension. That's changing from the small area approach to a more geostatistical approach. So I'm going to show you guys what we are doing there. We did a priority index, but they're not using that. Before moving there, the next steps, what they want to do is to do something like this for all the communicable diseases. And we did these already for visitor leishmaniasis in the country. And with some parameters, with some models based, and also with their knowledge, we're going to try to classify the microregions into classes. Not only the priority, but we also want to do based on other parameters, which is the risk factors. We're going to put some thresholds there, and we're going to try to assign classes so they can do something more feasible to the whole country, not only in the state, but to the whole country. So here we did compare, based on two different models, the number of municipalities that they were using on their program and classifying as low risk and high risk. What we found was that they were underestimating the areas where actually the model was understanding it was high risk. And we validate this model, we keep following this model. So we're trying to do something very similar for lepto, and the long term is to aggregate all these diseases in one model. It's going to take a long time, but that's the long term idea. And then they say, okay, can we do something at the great state, the best state? Say, no problem. They got the cases, they got the location of the cases. So they got all the location of the cases, of human cases, and we designed a case control study. Familiar with case control study? Case control, we have cases, and then we're going to compare to some number of controls. We want to try to keep the same approach that we did for this other model. So we decide to go for Gaussian random fields, which basically the structure of the random factor is the same. It's all Markovian. It means the distance between the neighbors is very important to recover the structure of the risk. Anybody familiar with Markovian? More or less? I'm not going to get too much here, but it's a very basic model. In this case, we only had the location of the patients. We have a logit, and we have an intercept, and then we have this random effect, which is depending on the distance between the locations. And this random effect has a 0 mean and follows a Gaussian process, which is basically a complicated process, but it's the same structure of the model that we're fitting at the small region, the small area approach. And here's how the covariant function works. It's basically depending on the distance between the points, and then we have some smooth parameter. We have also a precision, and this is going to depend on the distance between the points. So basically here what we have the case, so the location of the cases and the controls. The cases are all the observed cases in this region, and this is lat long transforming UTM because we are measuring the distance between the points. And then we went to the system and we random select for each micro region, or each of these little bit larger region, 4 controls. So we have unbalanced case controls. So we have one case going to be compared to 4 other controls. So what we do, we just put on top these locations, and then we run that simple model which is complicated in the background, and we are trying to recover then the risk or the structure of the risks in this space continuously. So we can, in the future, what we can do is we can predict this to a grid 1 by 1 kilometer, for example, and then we can give them very precise estimation of the risk. Okay? So here's just more how these cases are distributed. Red are cases and green are control. They're all over the place, and we have a big lagoon here, which is a little complicated here for this model, and this is going to be the next steps. Question? No? And we fit those initial models, and here is actually our posterior distribution, and what you can see is the mean posterior here and the standard deviation. So what we're going to do now, we're going to cut this layer into the microregion, and we're also going to project this to a grid 1 by 1 kilometer, and then they're going to have more exact locations where they can look for the bacteria. And the idea here is also to try to see and include other covariates, for example, density of domestic animals, cattle, horses, cases on dogs. So we have this data. We didn't include here. This is basically just the cases so far. And then finally, what we are moving next is try to really do a little bit things that are more realistic, but it's not that straightforward, which is basically try to model this at the non-stationary approach, which basically says that we have a barrier here, we have a big lake, and we know that people are not living in this lake, we don't have rats living in the lake, so we should not just model the Euclidean distance between these points, but really we should model the impact of this barrier in the risk. And here's an example of how this would look. So this is basically amount of fish in a study area, and a stationary model would just recover the posterior like this, so would just neglect the barrier. So what we're saying here is that we can fish in the ground and we can find fish, which is not true. We should really assign the barrier here to recover our posterior, and then the posterior should look like this, should really impact by the barrier. So we can build a triangularization in the barrier and then model this non-stationary process here. And this would depend on the size of the barrier. So we can see here we have a very large barrier, so we need to assign for it, but we have some locations here where we have a small barrier. So they're going to disturb our process a lot. So this is where we're moving next, and this is not going to be possible so far for the whole country, so we're going to do this for each state. As funding comes, we're going to do that for each state and try to really help them to go to a fine resolution and to really look for the cases, go to the hospitals and really confirm is there not a case there. And we are doing for lepto right now. The idea is to move forward for other diseases that are increasing in the area. For example, dengue it's just started to happen in this state, unfortunately, but throughout the country is a big problem. That's all I had for today. So if you have any questions, here's my email. Hopefully it's not too hard on you, but that is where I see we are moving. I'm a vet, so I'm also interested in more in zoonotic diseases. So I'm trying to apply these approaches to domestic animals as well. So we're doing something for the swine industry here in North Carolina, which we're trying to do something similar, but still ongoing process. Okay? Thanks so much. Questions? Easy, please.
Thanks, that was really interesting. did the controls there at the end,
Mhm.
the control locations meant to represent kind of that underlying population?
Mhm. So the controls that were matched by sex, age, and income as well. So we matched them by a couple of parameters.
Okay.
So there were people that went seek for help and they were not positive for lepto. So they were for anything else. So they were.
So then the prediction was kind of like the probability of people being sick relative to the controls?
Yes.
Is that right? And then I guess, maybe I'm not interpreting it right, but then did you do something to like scale the probability up to the population level? Was that like another step?
And then we are just predicting to the area, to the grid.
Uh,
So predicting to the grid cell, 1 by 1 kilometer. That's the final idea.
and that represents like the probability of infection.
Exactly.
Overall.
On that grid, yeah, that's the idea. And we are depending on this distribution of the locations because we know we have very large rice plantation in this area. In this area here we have very large rice plantation, and we know there is some very important structure of the risk here, more cases, but we don't have a lot of health units in this area. So we're trying to also see if that's a big impact. Try to include the accessibility of health also as a driver. We don't have it here yet, but we're trying to go that direction.
Okay. And then one follow-up question. I've heard of point pattern models
Mhm.
and played around with them a long time ago. I'm not that familiar with them, but did you consider a point pattern model as an alternative to this?
Yeah. We're just trying to, what we're trying to do here is just stick with the Markovian random effect structure because we did the other layer on that. So, but that's totally fine. We could do that as well. The idea is not to predict the prevalence, but try to recover risk. So to highlight, we don't have number of cases, so we cannot really say we are predicting the prevalence, but the risk. So if we had the number of cases per household, then we could try to approximate the prevalence and then see where the expected prevalence would be above a threshold. So that would be a next step, but we don't have the count number of cases. We just have location, yes or no. That's a limitation. It would be nice to do a cross-sectional study like they do for malaria, for example. They go to household, they draw a sample, they do a questionnaire. That would be useful, but super expensive to do it. Questions?
Yeah, thanks, Gustavo. What are your thoughts on possibilities for forecasting spread and persistence of disease in future years?
So in this case, if we had the projection, we have temperature and precipitation, that would be something we can do. We are just, right now, they're kind of behind on making decisions. So if we project for next year, they're going to take 6 months to make a decision to assign the money. So it will not be very helpful. But to do a forecast would be something that would be useful. We're trying to do that for other diseases, but it would be something useful to do. But we don't have the projection for the income, those things. So we just hold that still or multiply for some index and then.
Yeah, I could focus on environmental change.
Right.
Could be predicted.
Right.
Yeah,
Yeah. No, that's a good idea.
we should collaborate on
Okay. Yeah.
So what we're doing studies like these, and we're identifying potential risk factors.
Uh-huh.
The value in it is really that we have some political will to actually act on
Mhm.
what we identify. What you found most effective for conveying to those politicians, local officials, what formats? Through data, visual imagery, it's helping you convey what you need to generate the political will.
So this is totally political. They had complaints, and actually the son of a governor on one of the states got infected. So then they started the whole process. So they contacted us after that. But for the whole country, for example, for visceral leishmaniasis, they see it as a problem, and there is a big issue with the dogs right now as well. So it really depends if that things go to the media, and then the media catch attention, and then they go pressure them, then they look for help to do something. But proactive, if they will look for help, I don't think so. They are trying to do what they can. They are limited on staff, and it's hard to communicate with them, even though they are trained, they have training, but they've been in this position for so long, they were doing red tape for so long that they really, if they need to think too much, then it's okay, not interested on that. So that's why we're trying to come with something very simple. They can look a list, Excel list, priority, not priority. Okay, let me do this. If they need to make harder decision, then they tend to just, okay, thanks so much, but we're not going to use. That's what I see in that country. I know in other regions how it works.
Two-part question. First, is there any seasonality in any of the diseases you're studying? Like, do you see some type of seasonal trend in the number of cases reported? And you said there is a shortage of hospitals in some areas. Is there some type of correction for sampling bias due to that lack of hospital that you have done throughout the study?
Right, and we see a seasonality here. I didn't plot here the temporal effect because it's very complicated to interpret that. But overall, we see an increase in the trend on the structure effect, so it's increasing. It's not showing decrease, so expect this to go up still. So this is seasonality, and seasonality is going up on the posterior estimation that we have. And we are trying to put here and calculating the distance between the location where it happens to the health unit. But then the problem with the health unit, sometimes they don't have an MD, they only have a nurse. So a nurse is not really trained to identify lepto. So now we're trying to make a decision, what is a health unit? Has an MD, doesn't have an MD. And then try to really assign that to the model as a covariate to see if that's important. We did that before. We're looking at, we measured the distance and everything. Apparently there is a correlation, but we didn't have it here yet. It's a big problem because, they might have MD today, next week, just moved, and they move a lot down there. They look for a better job and they just move. More questions? Yeah.
Do you have the similar problems in the surrounding countries that this would be usable, duplicated?
So we are looking in Uruguay now, but the problem in Uruguay is that they have a paper record, so they don't have it in Excel, so it's very hard to help them. But they were concerned because we did something for our disease in this state as well, and apparently Uruguay has very similar conditions. So they might be, and we blame them for things, right? They are giving us disease, we're giving them disease, so there is this fight. They don't really want to hear too much. One example, FMD, which is foot and mouth disease, outbreak happened in 2001 in this region. We blame Uruguay, Uruguay blames the country, so it's a fight there. But the problem there is the data. They have very good data for cattle. They have a track system. They track all the cattle since they are born until they're slaughtered. But for people, they're behind. So if you're looking for cattle data, Uruguay is the best. And it's true. They really track every cattle, but human they are behind. More questions? Yeah.
You said you're doing this for the future too, so you have the information on the what management or what interventions they've taken in these areas to be able to see if that's had any meaningful effect on other cases that they're trying to see if they're actually being effective with their campaigns.
So we don't have that, and the idea was we're working with Brian Rich from Stats to try to optimize the treatment in space to see which treatment should be really deployed there, because right now if I tell them, okay, more education, how many schools they need, right? That's a big investment and I don't think they would do it. But for the collect of garbage, for example, they see that's a big impact when they do collect more trash and they don't have strikes from the companies. They see a reduction number of cases. This year in a town that I know very well, they have already 30 cases and the expectation was to be only 2. And what happened in that town was that the trash, they striked for 6 months. So people were just taking the trash or either in the street or just driving the trash to this dump. So it was a big issue there. Just one town, right, as an example. I cannot talk about the whole country. And that increased the cases. So 30 cases, I think they have 34 this week. And maybe is a bias, but it would be very funny not to be associated to that. And some regions also, they have tobacco plantation and corn plantation, and those folks are very exposed to mice and rats. And we also not considering this here, and we understand that that's an important factor to consider. There's another difference on the cases on the urban areas and rural areas. Urban areas more exposed to the water due to rain and everything, and in the countryside is exposed to be in a barn, to be exposed to the mice there. And one suggestion from these folks in the state was just to give more cats. So provide cats to these farmers so they could control the rat.
So the cats don't get infected with this?
Yeah, they get infected. They can get infected. They can shed. But then the rat is gone, right? It's a solution that they found. I guess they have too many stray cats down there. I guess they were just trying to get rid of them. So cat they can shed in the environment as well, the bacteria, but a rat, they replicate it more, right? It's much more of a problem. I like the idea, but it's not going to solve anything. But that was a suggestion of someone that was thinking, like, why? I think she was working with cats or just donating cats. Hey, I have cats if you want. Practical solution. Okay? Thanks so much.